So our last unit is atomic physics, and I want to start, I guess, by letting you know that this is where physics starts to merge with chemistry a lot. We're going to talk about what stuff, matter, looks like on an atomic level. And so we're talking basically, first we're going to talk about atoms. So I mean basically everything on the periodic table, hydrogen, calcium, lithium. But physicists, once they started figuring out, I almost probably shouldn't even say physicists, because it'll be physicists and chemists. Really, scientists in general, they weren't like one or the other, you know what I mean? Once they started figuring out the properties of hydrogen, then the questions were asked, well, what's smaller than hydrogen? And then they started to figure out things like protons, neutrons, and electrons. And now physicists are starting to work on, well, what's smaller than electrons? And what's smaller than that? And what's smaller than that? And, I mean, this is a never-ending cycle where you're trying to figure out what our Earth is made out of, basically. So there's going to be a lot of chemistry overlap, which is good because I think I teach all of you chemistry with one exception. So if I lose you on any chem stuff, let me know. But there's going to be a huge amount of overlap. It actually works out really good because for you guys in my grade 11 chem class, we're going to do a flame test on Wednesday in class. And we're actually going to talk about the physics behind why the flames burn different colors in physics as well. And for you guys in my grade 12 class, we're doing organic chemistry, where we talk about different ways that we like draw the models of like carbon to hydrogen and stuff like that. And we'll actually talk a little bit later on about valence orbitals and basically why the electrons spread out the way they do. So there's a huge amount of overlap, which I think is awesome because I'll try to relate it to between classes. Does that work? Okay. One more thing before I kind of start with the notes. I just quickly snapshotted a picture of your formula sheet. I just kind of want to walk you through the formulas that we have left to cover. Yeah, basically we need to cover a few up here. That's what it. Well, an E equals mc squared is one that maybe you've heard before because it's Einstein's pretty famous formula. This is energy, mass, and the speed of light. And we'll talk about that when we do fusion and fission. Same thing with this last one over here. But pretty much math-wise, we've actually covered nearly everything you need to know for math. So this is going to be a very theoretical unit. In looking over what limited diplomas I can look at, because this is a fairly new unit. They didn't really have this content in the previous physics curriculum, mainly because we're still kind of working on some of the new age stuff. It's mostly theory. Memorization of scientists actually is what I'm going to recommend you focus on. So when we talk about Rutherford or we talk about Thomson, make sure you know all these scientists because I feel like that's probably more what you're going to get assessed on rather than some sort of math question. Okay, today, tomorrow, and Wednesday, we're basically going to talk about the history of chemists and physicists trying to figure out what subatomic particles were. And like I just finished saying there, for the most part, there's no math. I need you guys to memorize physicists and chemists and know what they did. Okay. I remember seeing one diploma question where it was a numeric response. They gave a list of physicists, and then they also gave a list of experiments. And the question basically said, give an example of a physicist, give an example of an experiment he did, and then give an example of the physicist who came after him who revised his work. And so it was really open-ended because there was actually more than one answer, which was kind of terrifying in a way. Let me say that one more time. They gave, basically it was a numeric response, and using numbers like 1 to 8, like probably the first 4 or 5 were names of physicists, and then a couple of numbers were like some of their models or their experiments. And the question said, give a physicist, give an experiment or a model associated with that physicist, and then after that, give a physicist who came after that person who revised their experiment or their model of the atom. I know, a little open-ended. So let me walk you through some notes. I'm going to do my best not to read directly off my slides because I always hate that, but I'm probably going to do it a lot today. So here's where we're at. By the turn of the 20th century, so we're talking only 100 years ago, because you guys know how that works, where like 20th century is really like the 1900s.
Why?
Because basically the first century would be like from 0 to 100. Yeah. Therefore, the second century is from 100 to 200. So, Anyways, long story short, we're talking only 100 years ago, which is pretty recent in terms of physics. Physicists thought they knew what they were talking about. And I've kind of hopefully shown that to you in some of the previous lessons, where they thought they knew all this Newtonian stuff. So if I throw an object, they would know how it would land. If we were talking about celestial bodies orbiting the Earth, we lost you. Guess we'll have to start over. A little bit.
I think they have to go to the line.
Yeah. Awkward. Just wait here. Well, maybe while I wait for them to rejoin, I'm just going to keep talking here because... Oh, there you're back. Perfect. Wait, I mean, you guys can read this. I mean, the first paragraph there, I thought this was fascinating. You guys remember talking about Max Planck, because he basically came up with one of the most groundbreaking things in physics, his constant H, which was applied to, like, energy is related to frequency. Okay. I thought this was a crazy story. He wanted to figure out whether to go into music or physics. And he was advised to go into music because you will never get a job in physics because we know everything there is to know about physics. And boy, how wrong were they? Because I mean,
He came up with.
and not only that, the more we, at least for I know for me, the more that I learn about physics, the more I realize that we really don't know what's happening yet. Like there is so much that is unexplainable. Like for example, that double slit experiment. I mean, it is mind-boggling to me, the idea that if you shoot electrons through those two slits, and you don't look at it, and you just look at the results later, it gives you a interference wave pattern, meaning therefore electrons behave as waves. Okay, I can accept that. And then, remember watching that one video, the guy said, well, then they put a detector to see which of the two slits it went through. And as soon as they looked to see which one it went through, well, then the superposition kind of broke down and it went through either one or the other. And then they unplugged the detector, left the detector there, and it went back to an interference pattern. And nobody understands why it's doing that. I mean, it basically seems to be that if you look at electrons or you try to test their presence, they aren't in multiple places at once. But other times they are in multiple places at once. And we're going to talk about that on Wednesday when we talk more about the quantum model. And this is some crazy stuff. I love that quote by Richard Feynman. I think it's safe to say that no one understands quantum mechanics. So if by the time we're done talking about the quantum model on Wednesday, if you don't understand it and I kind of say, okay, do you get it? If the answer is no, that's probably good, because if you actually do understand it, you need to go on in this field, because very few people in the world can really wrap their heads around what's happening in physics these days. So, okay, so anyways, our goal today, tomorrow, and Wednesday is to talk about the history of physicists and how the accumulation of thousands of years, maybe not thousands, but at least hundreds of years of scientists trying to understand our universe has led us to the point where we're at today, where we think we know what's happening, kind of maybe. And that's going to come up a lot, especially in some of the videos I show you, where I think it's fair to say that in the history of science, here's a really great example. I've used this before. Galileo believed that the Earth was not the center of the universe, but that the sun was the center of the universe, and that the Earth went around the sun. But the Catholic Church believed the Earth was the center of the universe, and the sun went around us. I told you guys this story before, right? Galileo was correct, but he had no way of proving it. And they threw him in jail, basically, for the rest of his life. He was under house arrest. I always like that example because it illustrates the point that you could be the smartest person in the room, but if you can't get your point across and convince somebody else, then there's no value in it. But there's a great example, though, of scientists, other than Galileo, who, backed up the church. They thought that that was the way the world worked. They thought the Earth was flat. And there's been, hundreds, thousands of times in history where the scientific community thought one thing was true, and we've since discovered they were wrong. Or at the very least, if they weren't wrong, they were only, kind of right, but kind of wrong as well. Does that make sense? So, okay, let's move on here. Getting off track. Here's what I need for you guys to know, and we're going to work on these over the next 3 days. Today we're going to talk about Dalton, Thomson, and Rutherford. Tomorrow we're going to talk about Bohr, and then Wednesday we're going to talk about the quantum model, and I put question mark here to imply the idea that we're still working on this. By me, I don't mean me or you, actually. Maybe you. But physicists out there somewhere are going to be trying to figure out what the heck stuff is made out of. Alright, so let's start at the beginning here. In the 1800s, John Dalton basically was expounding on ideas that old philosophers from the Greek era had regarding matter. They thought that matter was made out of atoms. A few of you guys, no. Were any of you in my Science 10 class? Heather, were you in my Science 10 class? You were in the other half. Raj was in that group. Sometimes I talk to my Science 10s about this. The word atom, like A-T-O-M, in Greek is derived from the word indivisible. And so Greek philosophers basically had this idea that stuff, whatever it is you're looking at here, must be made of indivisible particles at some level. Imagine the idea that you have a cookie, and you rip it in half, and you rip it in half again, and you cut it in half again. Well, there's got to be a point where that little crumb you have there, if you sliced it in half, eventually you can't slice it in half anymore, because something is the smallest unit of matter. Does that make sense? So, I mean, ancient Greeks from the time of like 300 BC knew about this. And I mean, slowly over time they developed the periodic table by recognizing, well, one of those indivisible pieces of matter is hydrogen, and another indivisible piece of matter is copper. Does that make sense? So John Dalton basically worked with this idea and came up with an idea called the solid sphere model. So this would be a good example of like when I gave that question on the diploma earlier, you could say that John Dalton was involved with the solid sphere model. Okay. And then afterwards we'll talk about who followed him. Okay. He basically suggested that all matter was made out of like a ball. Now this one right here is hydrogen. This one right here might be larger perhaps, and maybe it's a different color, and this one is copper. And basically all matter was made out of just a small little ball. In my mind, I always think of, you guys know those little like magnetic little balls that are like really, really small, like buckyballs or something like that you can make different shapes out of, that you shouldn't give to little kids because they swallow and that's really bad. You guys know what I'm talking about though? Yeah. I always think of that, thinking like you've got these really, really small items, atoms basically, and I mean there's different shapes and different colors, but that's what stuff is made out of. Was he right? Well, he wasn't right. Was he entirely wrong? He wasn't entirely wrong either. I mean, he had an idea. It's kind of close, but I mean, here's one of his first problems. He couldn't explain how they were able to bond. So he wasn't able to figure out why this hydrogen, this oxygen, and this hydrogen right here, he couldn't explain why they would get bonded together to make, like, for example, water. So, I mean, he knew that small stuff existed, but it wasn't all the way there. So, on that particular diploma question I suggested, the follow-up scientist then would be J.J. Thomson. And so we're talking a little bit later in the 19th century, so late 1800s, scientists began experimenting with what are called CRTs. Do you guys know what cathode ray tubes are? Sorry, say that louder? Yeah, old TVs used to be made out of cathode ray tubes. You guys know like the big, like thick box type ones? They used to have cathode ray tubes. I've got a picture on the next slide of kind of what a cathode ray tube would look like. I mean, just from a physics point of view, not from a like illustrated point of view. The idea would be that you're going to shoot a particle, in this case an electron, through both a electric field. So the electric field has got a positive and a negative plate up top. And it's also going to go through a magnetic field, which is going, which way does X go? Good, into the page, yeah. And what would happen then is, depending on how these coils work, the particle will either go straight, or it'll go up, or it'll go down. Why would the particle go down? How could it be caused to go down? Well, that'll be due to the electric plate here. So you have the positive and the negative plate here. If this is an electron, which way is an electron attracted? Towards the negative, right? Oh, no, that's wrong. Sorry, the electron would be towards the positive. Sorry. I can't even read my own diagram here. The electron would go up towards the positive. Why does this go down? Well, a magnetic field would be pointing your fingers into the page with your left hand. Your thumb would be going to the left, and the palm shows which way it gets deflected. So it would get deflected downwards. Does that make sense? How these old TVs used to work then is they would shoot particles at like some sort of phosphoric screen, I imagine. I don't know what the exact chemical was. I want to think phosphate. And it would cause it to glow. So like this would be like the front of the TV screen, and basically it would shoot a whole bunch of particles at your screen, causing them to illuminate different colors. That makes sense? So anyways, back to these notes back here. Scientists were working with these cathode ray tubes, and they honestly, they didn't really know what they were doing. Like, they were playing around with them, kind of like a kid with a toy science set, basically like, hey, let's try this. Side note, I'm going to probably do this a lot today, where I'm just going to tell you random stuff that I know. You guys ever heard of Marie Curie? She worked with radium, and like a pretty famous female scientist. What was that? Yes, she did not know what she was doing. She was working with radioactive materials. She died from radioactive poisoning, basically. I mean, her stuff, like he said, her diary. You guys can go grab stuff while I talk. I'm just talking. No? All right, thanks, guys. Her diary, like her notes, are like quarantined because she was working with radioactive materials unprotected. You know, and I mean, she died due to the poisoning due to that, right? And I mean, that's a great example of scientists back in this era. They really had no idea what was happening. You know? So they just kind of played around with stuff, and then hopefully they learned something from it. So cathode ray tubes are a good example. They discovered that these cathode rays would move from negative to positive. Well, later we discovered that, I'm going to use quotes here, cathode rays were really electrons. But they didn't know that back then. They didn't understand what electrons were. All they knew was that particles, really, really small particles, were getting shot through these tubes and hitting a screen on the other side, but they didn't know what they were. They knew they were smaller than hydrogen, because hydrogen was like the smallest particle that we have. So they knew that, but they didn't know what they were. So I put a little note here. Cathode rays were actually electrons, but they didn't call them electrons back then, because, does that make sense? We know they're called electrons because we teach you that. But they didn't know this. So Thomson basically attempted to figure out whether they could separate the cathode rays from the negative charges. They knew that these cathode rays were negatively charged, but they didn't realize that the cathode rays were because they were negatively charged. They thought maybe the rays themselves had something in them that they could like separate, if that makes sense. Like I kind of imagine like thinking, I don't know, it's like Star Trek and there's like a phaser, but something inside the phaser can be separated out. And no, like it was just a stream of electrons. So, long story short, though, he did something very important. He calculated the charge to mass ratio for an electron. And I'd like to do that right now here. What is the charge of an electron? Okay, now at the time, they hadn't found this number yet. We hadn't actually found this number yet. And he also, the mass of the electron, you guys know, we know what that is now in hindsight, right? It's 10 to the minus 31 kilograms. So if you guys have a calculator, can you guys divide these two numbers here? What'd you get, Sam?
1.76
times 10 to the 11. Okay, that'd be joules per kilogram. Okay, this is a constant that Thomson was able to calculate. Here's the problem, though. He didn't actually have either of these numbers. So later on, when we actually found the charge of an electron, that's actually what allows physicists to figure out the mass of an electron. But all he was able to do was calculate their proportion to each other. Does that make sense?
So we said
Yeah. But he didn't know these two individual numbers, but he was able to calculate this number. I'll show you how on the next page. So what he did is he set up these fields, one electric, one magnetic, so that the electrons, which he didn't know were electrons, but
Miss Bicheval, can you please call 100? Miss Bicheval, please call 100.
so they called them cathode rays because they originated from like cathodes. But he didn't actually know that they were electrons yet because we didn't have that term. But basically he set it up so that some would deflect upwards and some would deflect downwards. And he finally figured out a way to adjust the dials of both the voltage and the magnetic field. So eventually they went perfectly straight. So what does that mean if they go perfectly straight? Well, it means that your electric field must be equivalent to your magnetic field. That makes sense? Now, they didn't know at this point yet what the charge of an electron was, but they did understand about charges in general. So they had these formulas already figured out, that electric field strength times charge is equal to force electric. That's off your formula sheet. And they also knew that QVB is equal to magnetic force. So the actual charge got canceled. And basically what they did then is they divided out B from both sides here, and he found a velocity. Now, he didn't have a way of measuring how fast his electrons were traveling, because it's not like he has like a radar gun that he can shoot at it like a cop would shoot at you when you're like speeding. Does that make sense? So he had no way of actually knowing the velocity of these things, but he could calculate it by manipulating the electric field and the magnetic field, and he found out how fast his electron was moving. Does that make sense? So this electron might have been moving at like, say, I don't know, 1.5 times 10 to the 7 meters per second. I'm just going to make up a number. And if it was moving that fast, then it would go straight. If it was moving any slower, it would go like, say, up. If it was moving any faster, it would go down. So he found the velocity. Okay. Well, then on the next slide here, once he had that velocity, he turned off the electric field. So if you turn off the electric field and only leave the magnetic field, it's going to deflect downwards. But he actually deflected it so much that they got trapped in a circular path. And we've done calculations on this before, where now it's going to start traveling in a circle, and he was able to then put other formulas together. The magnetic field now is equal to centripetal force. Does that make sense? And he did some rearranging here, where, well, magnetic is still equal to QVB, centripetal is equal to mv squared over r, so he canceled one of the velocities. Took the B from down here, plugged it on the bottom, took this mass right here, put it on the bottom, and basically found a formula that would get him charge over mass. And all he needed to have were three values: a magnetic field strength, which he knew because he was manipulating it, a velocity, which he also knew because he had just found it from his previous calculation, and a radius, which all he had to do was then measure, well, how are his electrons going around in a circle now? And so it was pretty clever. He managed to find the very first charge to mass ratio. There's a decent chance you'll be asked to find a charge to mass ratio on a diploma question. So we're not really adding new formulas. We're just using the formulas that we've already talked about. Okay. I actually gave you a question on this on one of your tests before, where I asked you guys to figure out which particle it would be based on charge to mass ratio. And like your choices were proton, neutron, electron, alpha particle, I think. You guys remember this question? It's not an exam or a quiz like 2 units ago maybe. So at this point here, we have the ratio of charge to mass, but they didn't yet know the actual charge, and they also didn't know the actual mass. They just know how they compared to each other. And this was kind of unique because it was a very highly charged particle with a very small mass. Think about other particles they might have known about in that day. They might have known about, say, something like sodium positive. There is a positively charged atom. Its charge would also have been 1.6 times 10 to the minus 19. They wouldn't have known that at the time, but that's what its charge would have been. But how much mass does sodium have compared to a single electron? Way more. Does that make sense? So what basically Thomson was able to figure out is that there are particles out there that are really small that have a lot of charge to them. So smaller than anything on the periodic table. That's what he's able to figure out. So I just wanted to point out here, he figured out the mass charge of the electrons. They weren't called this yet, but this was the start of the understanding that subatomic particles were very low mass, very high charge. Does that make sense? Like I said, it's a lot of theory today. Not even theory, like history, I guess. So here's some conclusions Thomson made. So, first one, this charge to mass ratio was bigger than any previously known ion. So that's what I was kind of just trying to show you. Like, they knew about calcium ions and hydrogen ions. This guy right here has like 2 for a charge. But when you're dividing it by its mass, like the mass is massive. Right? Same thing with even hydrogen. So they were super concentrated. He actually had a name for them. He called them corpuscles. Yeah, that didn't stick. We eventually called them electrons. He also thought that atoms were entirely made up of electrons. He thought he was right at first, but he eventually realized he was wrong, because he realized that if everything was made up of just electrons, just negative charges, that's not going to work, because you're going to need to have at least some sort of positives to balance them out. And they knew that because they knew that atoms could be neutral. Because they knew there were some atoms that didn't have charges. Does that make sense? Like, they knew there were some atoms that could have charges.
Kyle Blood, can you please come to the office? Kyle, please come to the office.
But there were some atoms that were discovered that were completely unreactive. Do you guys know which atoms are completely unreactive? The noble gases, yeah. So he knew that there must be the possibility that there were, like, for example, helium or neon or argon, right? Those guys right there, they're neutral. They would never react either positively or negatively. They were always in a nice state of balance. So they knew that neutral molecules must exist, or neutral atoms must exist. So therefore, he realized that if he thought that they were only electrons, that had to be wrong. So here was his suggestion. He called it the plum pudding model. And the reason he called it plum pudding model is because, like, in England, that was a pretty common, like, dessert, I guess. So I've seen other examples where, like, think of like a cookie. So here's a cookie. And he suggested that, like, the bulk of the cookie was positively charged. So that would be like your dough, basically. And within that cookie were, like, chocolate chips. Or in the plum pudding model, it was raisins, I think. And all of those things are like negatives kind of spread around. And he figured, well, as opposed to Dalton thought that there was basically just like balls. And that's all it was, like a billiard ball, basically. Well, he suggested that an atom was a little more complicated, that it had like a positive like fluid running throughout it, and that interspersed in that fluid are negatively charged things. Is he wrong? Yeah. Did he have some elements that were correct, though? Yeah. I mean, there are electrons spread out throughout atoms, but it doesn't really look like this, at least to the best of our knowledge. Does that make sense? Okay, so next scientist I want you to know about. Now, Robert Millikan, we've actually talked about before. He didn't actually produce a model of the atom. So if you guys get asked that question about scientists and like one that like say comes after the previous one, don't include Millikan because he didn't actually suggest a new model of the atom, but he did an experiment that was pretty influential. And we've talked about this before. He did the Millikan oil drop experiment. You guys remember researching this in the like 2 units ago now? Basically his idea was you're going to shoot some sort of charged oil.
Please excuse the interruption. Will all Blood Tribe students please come to the office? All Blood Tribe students, please come to the office.
All right, so you shoot some sort of oil, you give it a charge, and you suspend it between 2 plates. And what should happen is the gravitational force pulling you downward needs to be equivalent to the electric force keeping you suspended. And basically he did this formula here where like Fe equals Fg. Holy smokes.
Sorry. That's all grade 10 through 12 Blood Tribe students. Please come to the office. That's all grades 10 through 12 Blood Tribe students. Please come to the office.
Okay. So you guys can hopefully follow this math here. Basically it was the electric force equals the gravitational force. So Fe is equal to Q times the electric field strength. But electric field strength is actually your voltage over your distance. So he found a way to basically figure out charge. Charge was dependent on mass. Now, this was not the mass of an electron, this was the mass of the actual oil drop, which he found a way to weigh. G, gravity 9.81, you can find that. D, the distance between these two plates, you can measure that. And the voltage, which he manipulated until he got it to the point where these things hovered. And he found the charge. Well, this is really important, because remember how Thomson had just found the charge to mass ratio? Well, Millikan found charge, which then meant that physicists could then know the mass of the electron. Does that make sense? So Thomson found the charge to mass ratio. He didn't know either the charge or the mass, though. He just knew what the ratio of the two of them was. Millikan found charge, so therefore if you have charge, now you can work backwards and find mass. So that's kind of what I read about here. Millikan was able to determine that all the charges seems to be multiples of 1.6 times 10 to the minus 19. So he basically figured, well, that must be the smallest charge possible. And so he called it E, the elementary charge, which we still put on your data table. And then the last thing I wrote here, and it allowed them to figure out the mass of the electron.
Based on that charge to mass.
Based on that charge to mass ratio that we had just calculated. Okay, so the next physicist I need you guys to know about is Rutherford. He would probably be the next one who actually proposed a new model of the atom. I just want to throw Millikan in there because he was pretty important. He helped us find the mass of the electron. But he didn't actually propose a new way of thinking about what atoms looked like. So Rutherford was also curious about what atoms were made of, so he shot alpha particles. We've talked about alpha particles before. Do you guys actually know what they are, though? Okay, so an alpha particle has 2 protons and 2 neutrons. Well, I think I've taught pretty much all of you chemistry. What else has 2 protons and 2 neutrons? What? Helium.
Oh.
Yeah. This was helium. But it was helium without its electrons somehow. So it's almost as though you took a helium particle and you just took the nucleus of it. Now, they didn't know about nucleuses at the time, because they weren't even to that point yet. But basically an alpha particle is a helium nucleus, which basically involves, like, you know how you'd have like proton, neutron, neutron, proton, like all in a nucleus, and then you'd have like 2 electrons around it, and that would be helium. Well, rip off both electrons somehow, and that's an alpha particle. One of the, I don't know, maybe cool things about this is, again, Rutherford didn't actually know what it was at the time. He knew that alpha particles were a really small particle, but he couldn't explain what they were because he couldn't look at them. Oh, another side note I want to bring up. I forgot about this one here. Microscopes. Why didn't scientists just look through microscopes? Well, okay, so a couple of main reasons. I mean, did microscopes exist? Sure. Biologists were looking at cells underneath microscopes for years. Like Robert Hooke came up with microscopes. I want to think it was him, or was it? No, Robert Hooke came up with the idea of cells. It was Van Leeuwenhoek came up with the microscope back in like the 1700s, I think. So like they knew about microscopes, but microscopes were based on light. And the wavelength of light basically limits how good your light microscope is. Nowadays, do you guys know what we make our best microscopes out of? Electrons, actually. Some of the best microscopes in the world now are based on shooting electrons at things, and as those electrons either bounce or deflect or ricochet off of matter, that's how we get a picture of stuff under microscopes. The problem we have here then is this stuff is so small that even to this day, electron microscopes are not all that useful. Because if you want to shoot, like, say, electrons at something to see what it looks like, what if you're shooting an electron at another electron? How good of a picture is that going to provide you? Not very. Further to that, we actually even talked about this in the last unit, the Heisenberg uncertainty principle, that basically suggests that as soon as you start looking for an electron, it will be gone. The mere presence of looking at something, the light bouncing off of that electron and getting deflected to wherever you're at, is going to actually cause the electron to go somewhere else. Should I reiterate that point? If I were to, like, say, try to figure out where Justin is, I could look at Justin, sure. But let's say I was a microscope. I might throw a ball at Justin instead. And if it went over there and it didn't deflect back at me, then I misjusted. And if I threw it over there and I missed it, I wouldn't hit Justin, right? But imagine when I was shooting a ball hits Justin and bounces back at me. Well, that might be how I detect Justin's presence. Does that make sense? Well, that's kind of what light does. Why do I know that Justin is there? Well, I can see him. But really what I'm seeing is light bouncing off of Justin and hitting my eyes. Does that make sense? Now, Justin is wearing, say, let's not use black, because black's for example, but Justin's got like orange on the back of his shirt there. Well, the reason why I'm seeing orange is because that's the wavelength that is being re-emitted towards my eyes. All of the rest of the wavelengths are getting absorbed by his shirt, except for that wavelength. And so that's why I see blue, or you guys are all wearing really boring colors today, actually. Me too. That's why I see orange or green, because really what's happening is light is hitting that object, and that wavelength is the only one getting reflected back towards my eyes. Does that make sense? Black actually absorbs like all wavelengths, ideally, right? And we talked about black body radiation, which is where like a black object somehow turns different colors because you're heating it up so much. Still with me? So now imagine that Justin is not Justin, but now he's an electron. And so I'm doing that same thing where something is bouncing off of Justin and coming towards me, and that's how I perceive him. Well, now he's an electron, and light hits an electron. Well, what we learned in our last unit is if light hits an electron, it's going to cause that electron to move, to scatter, to go somewhere else. So let's say light hits Justin as an electron and comes and bounces towards me. And I think that Justin was right there. He won't be there anymore. He will have moved already. Does that make sense? And that's one of the biggest problems with trying to figure out subatomic particles is they are so small that it is impossible for us to find where they're at. That's where that Heisenberg uncertainty principle came, where we can either know kind of an object's location, or we can know how it's moving, but we really actually can't know both. We can't know momentum and position because they're related to each other. As soon as we pin down where Justin is, we don't actually know how fast, if we can find out how fast he was going, then we can't know where he's at. If we know where he's at, now we don't know how fast he's going, or we can't know his momentum. So, anyways, I had a point and I totally got off track here. What was my point? I guess, the original idea that we can't look at this stuff. Even to this day, we cannot zoom in close enough with a microscope. Because if our best microscopes basically involve shooting electrons at things and seeing how the electrons bounce off of those objects to make a picture of where things are. Think radar. You guys know how radar works? Like a submarine or sonar. Shoots a wave. If it bounces back towards you, then it can figure out where something is. Okay. Well, if our best microscopes, electron microscopes, shoot electrons at other electrons, how well is that going to work? It's not. Does that make sense? So, anyways, back to my notes here after I got super sidetracked. Rutherford was working with alpha particles. Alpha particles actually were being emitted by also radioactive decay, which he didn't understand at the time. But he actually was smart enough to put the radioactive decay in a lead box so that when it shot out alpha particles, at least it was shooting them in one direction, and the radioactivity was being shielded by lead. So I believe Rutherford didn't die of radioactive poisoning, but I don't remember. Anyways, he had Geiger. Maybe you've heard of Geiger counters before, named after this guy. They figure out how much radioactivity there is. And Marsden, these were his lab assistants, from what I understand. They helped him do the gold foil experiment. And let me just hop to the picture here. Lead box, radioactive sample inside, doesn't really know what it's doing just yet, because they didn't know what alpha particles were, because they were still working on what electrons were, for crying out loud. By the way, this is in 1917, so we're only talking 100 years ago. We didn't even know what electrons fully were. Shoots alpha particles at a very, very thin sheet of gold. Gold is really useful because gold can be hammered into sheets that are really thin, sometimes thin enough that they're only 1 or 2 molecules deep. It's a really cool property of gold. And basically what he discovered is as they shot these alpha particles towards the gold, sometimes they'd get deflected at different angles. They put a zinc sulfide screen around the edge of it so they could see a color, a flash of light, get emitted when it hit the screen. And they thought it was really odd that all of these particles, one, that they somehow went through, and two, why are they getting deflected? I have a better picture here? Yeah, here's a really good picture of what's happening here. They discovered that a lot of alpha particles, they went straight through. Some deflected a little bit to the side, and then some like bounced really off to the side. Here's the quote I wanted to point out. Rutherford described these results as saying it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and then it came back and hit you. Because that was what he discovered, is he'd shoot these alpha particles at gold foil. He expected most of them just to pass through, phase right through, and some of them would hit and bounce right back at you. You'd be like, how is this possible? Well, we now know it's because all particles in the middle of the particle has a very dense center called the nucleus. You guys have heard this before, I hope? That he discovered the nucleus, basically. He thought that everything would just phase right through. Do I have another picture here? I do. But here's what was actually happening. So I got two different pictures here. Here's what he expected to happen. Here's what actually happened. In the middle is the nucleus. Or at least he then hypothesized, well, there must be all of the positives all in one small location. And so sometimes it would hit the nucleus and bounce off a little bit. Sometimes it would phase directly through. Sometimes it would phase directly through. Here's an example, hits the nucleus and it comes right back at you. You'd be like, how is that possible? My Chem 20 class, we just finished talking about gases. One of the things we mentioned in gases a lot is the idea that in between gas particles, like here's a particle, here's a particle, here's a particle, what is in between these gas particles? Nothing. Like literally there is nothing there. You could consider there's a vacuum there. There's a lack of particles there. And that's what we were kind of discovering here, is that in this ball, think back to the Dalton model, Dalton thought that it was just a solid billiard ball. Well, now we've discovered that really there's like dead space in between there, where like right here, there is nothing there. There's not even electrons, there's not even protons, there is nothing there. Okay, well, physicists nowadays are working on concepts like things like dark matter, which I couldn't even begin to explain to you, but they have theories about in that empty space, maybe there actually is something there that we can't detect that's not matter, like antimatter or something like that. But to the best of our understanding, like there literally is nothing in some of these spaces. Make sense? Long story short, he came up with the nucleus idea. So this was his model of the atom. Sometimes we call it the planetary model. He decided that in the center of the atom should be a dense, very, very, very dense positive nucleus. So there's going to be a lot of positive charges all shoved together here. And surrounding them should be electrons, which is why those alpha particles could go through, or they could bounce off, or they could bounce back towards you. Does that make sense? Okay, here's a key point here. There were some huge flaws, though. One of the flaws I didn't write about is still something to this day that physicists are working on. Let's say you have a whole bunch of positives all stuck together in the nucleus. Do positives like to be next to each other? Why does the nucleus not just explode? Well, some do actually. That's actually what we're going to talk about later with like radioactive decay, fission and fusion, those sorts of ideas. There are some nucleuses that are unstable, and so elements will break down. But that usually happens when you get like to the really high numbers, like for example uranium or plutonium, stuff like that. So, but then the question lies in, well, why does an oxygen atom not just rip itself apart? You've got 8 protons right next to each other. So, it doesn't really have an answer for that. To be honest, we're still working on answers to that. I believe it has something to do with like strong nuclear forces. But here's the other major problem though. If electrons were moving in circular motion, like say electrons are going around in circles, well, anything that's going in a circle is going to have a centripetal velocity and a centripetal acceleration. You guys remember that from like our first unit? Well, electrons are charged particles, and if charged particles are accelerating, they should be giving off EMR. But they're not. So there's a bit of a problem here. According to Maxwell's theory of EMR, any accelerating charge should release EMR. Here's the other problem. It should then lose energy because if it's giving off EMR, it should be losing its energy. And so electrons should start spiraling into the nucleus, meaning that if you have electrons sitting out here and they are going in a circular pattern, which means if they're accelerating, they're giving off EMR, which is like what these waves are trying to show. Eventually, all electrons should spiral into the nucleus, causing all matter to like collapse in on itself. So I mean, here's a couple of big questions. Why do all these protons stay next to each other? Because they wouldn't want to, would they? And second question, why do the electrons stay way out here? Because shouldn't electrons want to be attracted towards protons? But yet they don't. So
Maybe Thompson was right that all just combine into one big.
one big like sludge of this thing right here. So that's where I'm going to stop today because I've already talked for about an hour. Tomorrow I'm going to talk about Bohr's model of the atom, and then Wednesday we'll talk about the quantum model. One thing I really need to reiterate though is that, yeah, there's a diploma exam I need you guys to study for, but I mean if you truly care about some of this physics stuff, it is still being figured out. And I think that's awesome. Because in 100 years, because think about this, the stuff we're talking about right now as being wrong was 100 years ago. What will we be teaching kids in school in the year like say 2115? To me that blows my mind. That like there is still so much out there we need to learn about how our world works. Alright, any questions? Okay, here's my recommendation then. I don't have any math or practice really to give you in this section, because to be honest, it's all scientists and history, and you will get tested on that though. I guarantee that. Like, you need to know all these scientists, you need to know what they accomplished, what they did. You may get asked to do some calculations on a Millikan experiment or on a Thomson experiment, but we've kind of already done that, where you do something where you make like say FC equal FM, or you make FG equal FE. So you might get asked to do some calculations on that, but the math on that is not new. We've already done all that. So here's what I recommend. You guys need to read your book. I know I say that sometimes, but here are the remaining chapters we have to cover. And this chapter right here that we're starting with is basically all about history. And you need to know that history. So I would recommend, if you're going to do something for studying, read through chapter 15.1, 2, and 3, because that's what we just covered. And then tomorrow we'll do Bohr, and then the next day we'll do quantum. That's the best advice I have for studying, because there's not really anything else you can practice, so to speak. Does that work? Okay, so go take a break. When you come back, find something to do for the next half hour.